All right, let's continue our learning talking about thermodynamics. So we have talked about enthalpy, which had to do with the heat involved in a process, in a system, maybe in a chemical reaction. And that tells us whether a reaction is exothermic or endothermic. It tells us whether it's releasing heat or energy, whether it's absorbing heat or energy. That's enthalpy. We talked about that quite a while ago. Then the last set of notes that we did, we talked about entropy, and that's the randomness of a system. So we said that randomness tends to increase. Now we're going to talk about Gibbs free energy. Gibbs free energy is kind of a combination of those two concepts, and maybe a little bit hard to define. We'll come up with or we'll talk through a few different equations, but also ways to evaluate this and to think through it. Gibbs free energy is the greatest amount of work that can be obtained from a substance. The way you find it, Gibbs free energy is equal to the enthalpy minus the temperature in Kelvin times the entropy, where H is enthalpy, as I just said, and S is the entropy, T is the temperature in Kelvin. So delta G is the change in Gibbs free energy. So it's the change in G. It's used to determine whether a reaction or process is what we call thermodynamically favorable. Historically, we use the word spontaneous. I want to emphasize this phrase because that is what College Board is moving toward. So in your answers, don't use the word spontaneous. They don't really like that anymore. They lean more in the direction of this term, thermodynamically favorable. I'm still including that spontaneous or non-spontaneous word a little bit in the notes because you might come across something that mentions the word. I want you to know what they mean by it. But when you're writing FRQ answers, you want to make sure you use this terminology, thermodynamically favorable or thermodynamically unfavorable. It also is a little bit more clear what we mean when you say this rather than spontaneous. Thermodynamically favorable processes occur without outside intervention. So it's a chemical reaction or a physical process, a change that occurs that does not require additional outside forces, outside action to make it happen after the activation energy has been reached. Thermodynamically unfavored or non-spontaneous processes occur only with continuous outside intervention. We'll talk about a couple different ways to do this when we talk about coupled reactions. But in general, a thermodynamically unfavorable process tends to not happen. It doesn't happen without an outside source of energy or some other form of intervention. When delta G is negative, that means the reaction or the process is thermodynamically favorable or spontaneous. Apparently misspelled something. There's an R missing. That's what it is. Okay. Thermodynamically favorable or spontaneous. Again, this is the word I really want to emphasize. Thermodynamically favorable. This also means that products are favored. When delta G is positive, the reaction or the process is thermodynamically unfavorable. You might say non-favorable, but unfavorable I think is preferred. Thermodynamically unfavorable is the main phrase we want to use. You might also hear non-spontaneous. That means that the reactants are favored. So the reaction going forward doesn't tend to happen. The reactants are the ones that are favored. Gibbs free energy and kinetics. So first of all, this kind of sums up Gibbs free energy. For it to be a favorable process, one that tends to happen, one that will happen without outside intervention, that is a negative Gibbs free energy. That's what makes it spontaneous or thermodynamically favorable, is for delta G to be negative, when the overall expression here gives you a negative answer. Now let's talk about it in terms of kinetics and some things we need to know about that. Delta G does not tell us anything about the rate or speed of the reaction. So kinetics and Gibbs free energy aren't really related. They don't really impact each other directly. So some reactions are very fast. That's like the combustion of hydrogen. It explodes. It's a very quick reaction. Other reactions are really, really slow, like graphite turning into diamond. But both of those are thermodynamically favored. Now that seems kind of crazy. Graphite just turning into diamond, that just doesn't seem to happen, right? Well, the rate or speed of the reaction is actually determined by the size of the activation energy. So if your activation energy is too big, that can make it to where the reaction doesn't happen fast enough for it to really even be worth thinking about. A large activation energy means a very slow reaction. And if we have a small activation energy, that means a very fast reaction. Remember, that's that bump on your potential energy diagrams. That's what activation energy is. So if the reaction is thermodynamically favorable, but does not happen at a measurable rate, so that's something like, we just mentioned that example of graphite turning into diamond. It's supposed to be thermodynamically favorable. Why don't we see graphite just turning into diamonds? If it happens, or if it's thermodynamically favorable, but it does not happen at a measurable rate, we can conclude that it is under what we call kinetic control. Kinetic control. That means that the activation energy is so high. The main reason for this is that the activation energy is so high that the reaction does not occur to a large extent. It hardly happens at all because the activation energy is too high for it to really proceed. Even though if that activation barrier were granted, it would be a spontaneous process. It just does not happen because the activation energy is too high. So we say it's under kinetic control. You might see some questions where a process is described and you've got to look at it and recognize this has a negative delta G. So it should be a spontaneous process. It should be thermodynamically favorable. Why does it not happen? And you will have to be able to say, because of the high activation energy, or because it's under kinetic control, it does not happen. It must have to do with kinetics, because the thermodynamics tell us it's favorable. So those are two separate things we have to consider. Not only whether or not it's thermodynamically favorable, but whether it happens so slow that it's not measurable, and that has to do with how high the activation energy is. Okay, and then we get into Gibbs free energy and equilibrium. There's another connection between this and a prior unit. Equilibrium was a tricky unit, but there's one thing that we're going to touch on right here. I hope that it rings a bell and that you definitely remember this. And that is that if K is greater than 1, the reaction proceeds to products. But if K is less than 1, the reaction favors the reactants. And I hope that you can remember that. That's really, really an important thing. If delta G is negative, so remember that delta G is negative from up here, that means a thermodynamically favorable process. Keep that straight. If delta G is negative, it's thermodynamically favorable, that means that the forward reaction is favored. It tends to happen. So the equilibrium constant has to be greater than 1. It has to be positive. It has to be greater than 1. The reason it has to be greater than 1 is because if K is greater than 1, products tend to be favored. Right? And that's what we just said. If delta G is negative, the forward reaction is spontaneous, or it is thermodynamically favorable. So the products are favored. That means the equilibrium constant, K, has to be greater than 1. But if we have a very small k, a fraction or a decimal number, if k is smaller than 1, that's when delta G is positive. If delta G is positive, the forward reaction is not favored. Instead, the reverse reaction is favored. So the equilibrium constant is smaller than 1. So K will be smaller than 1. Now, if delta G is 0, then K is equal to 1. And that's already at equilibrium, essentially. Calculation techniques that we're going to learn to use, and we'll go through these in a little bit more detail later on, but we'll be using standard free energy of formation from a table. Okay. Hess's law, we learned about Hess's law with enthalpy. We're going to bring that back in with delta G. Using standard cell potential, okay, and that's something we actually briefly talked about, using standard cell potential when we figured out how to do that with redox reactions, combining redox reactions together in order to get a voltage or a cell potential. And then using the equilibrium constant, K, of the reaction, there's actually a formula for relationship between the equilibrium constant and Gibbs free energy. And then we can use delta H and delta S values to find our Gibbs free energy as well.